As the last talk in this session, there will be a talk on Freenet, next generation. Probably most of you know Freenet in its earlier generation, back in '99, first anonymous, secure network, peer-to-peer. And now it is my pleasure to introduce to you Ian Clark and Oscar Sandberg, who are the originators of Freenet and its next generation, and welcome.
Thank you. Thank you very much. So my name is Ian Clark. I'm the founder and coordinator of the Freenet project. Freenet's something I've been working on since about 1999. This is Oscar Sandberg, who's our resident mathematician, or semi-resident mathematician. And the work we're about to describe is a collaboration between Oscar and I, and it represents what will be the next version of Freenet. So we've been in the peer-to-peer business pretty much as long as there has been a peer-to-peer business. Well, let me talk about the goals of Freenet first for those who are not familiar with it. The goal of Freenet is to allow people to publish and consume information anonymously. It's primarily designed for people living under repressive regimes in countries where the internet is quite heavily censored, particularly situations like China, where the path between points inside China and points outside China are monitored and controlled by a firewall. But Freenet also has its uses in Europe and in the United States in situations where people are unreasonably trying to limit people's ability to communicate freely. The original design of Freenet, and I'll talk a little bit more about this, but the original design was basically anyone could join the network. The algorithm that we use would select people for your computer to talk to, and through those connections you could push information into Freenet, or you could request information from Freenet. And the most popular user interface for Freenet actually is just a web browser. We set up a HTTP proxy through which you can request information from the Freenet network, and it just gets displayed in your web browser. However, what we have realized over the past few years is that when the act of participating in this kind of network in itself can cause people to get into trouble, the current architecture used by not just Freenet, but pretty much all comparable anonymity networks is not sufficient. The reason is that if anyone can just connect to anyone else, then how do you know that the person you're connecting to isn't the Chinese government or the state police? And if you connect to them, or they connect to you, then they know that you are participating in the network, and that in itself could cause serious problems for you. So we realized that in the future, for an architecture like this to be truly robust in a situation like China, or even in the United States with some of the court decisions that are now coming down with respect to peer-to-peer software, we would need to adopt a more closed approach whereby people only connect to other people that they trust, to people that they're okay with knowing that they are participating in the network. One word for this is a friend-to-friend network, or a darknet. The terminology is still kind of evolving. So taking a step back, what is a peer-to-peer network? Well, you'll almost get a different definition from everyone you ask, but probably the things few people would disagree with is that a peer-to-peer network is where you have information that is spread across many interconnected computers. Users of the system want to find that information. How do they do that? Well, the simplest peer-to-peer networks and the first peer-to-peer networks, for example, Napster, had a very simple approach to this, which was that you have a central database which knows where everything is. And so if you want to retrieve a particular piece of information, you contact this centralized database. You say, here's what I'm looking for, where can I find it? It tells you, and then you contact those other peers directly and request the information from them. Some approaches, the problem with that, by the way, is that if you rely on a central company or computer, then it can be shut down very easily or blocked. And indeed, that's exactly what happened to the original Napster. Some peer-to-peer networks are semi-centralized. The most popular example of that would be Kazaa, whereby instead of having just one central point, you have many of these central databases which know where to find content. So if you want to find some content, you basically contact your nearest super peer and they will tell you where to get it. The problem with that approach is that it has limited scalability. You're only going to be able to find information if the super peer or super peers you talk to happen to know about it. So it has a search horizon is another way to describe that. Other peer-to-peer networks are completely distributed. Freenet's an example of that. It's completely distributed in the sense that all peers are essentially equal. We don't have some peers that are responsible for keeping track of where information is, and other peers are just essentially clients. All peers do essentially the same job, and they all collaborate with each other in order to allow you to find information in a hopefully scalable and robust way. There's another way you can kind of break down peer-to-peer networks, which is will get us onto what we're describing here. Light peer-to-peer networks, which basically almost all peer-to-peer networks we would describe as light peer-to-peer networks. A light peer-to-peer network is a network where anyone can connect to anyone else. You sign up to the network, and depending on how the algorithm used by the peer-to-peer network works, you can end up talking to anyone. It doesn't care. It's effectively promiscuous. The advantage of this, well, it's relatively simple to implement, provided you're using the right routing algorithm, the right algorithm to allow peers to find the information they're looking for. The disadvantage, it's vulnerable to what we call harvesting, this process whereby someone that you don't want to know that you're part of the network can find out that you're part of the network and perhaps punish you for it in some way. The other alternative is dark or friend-to-friend peer-to-peer networks where peers only communicate with other trusted peers. The only real working example of this that we're aware of, I think, is a piece of software called Waste that many of you might be familiar with, where only the people you trust know that you're part of the network. But the problem with Waste and the Waste kind of architecture is that if you can only get information from your friends, then Waste peer-to-peer networks tend to be small and isolated, which really isn't terribly useful for the type of things that we want to do, because we want to allow people to share information with anyone else that's interested in it, not just with the people they know directly. So how does a network like a peer-to-peer network like Freenet or peer-to-peer or distributed hash tables, which is another class of peer-to-peer application, how do they find information in a decentralized, scalable way? Well, they rely on a principle that you're all probably familiar with, the small world phenomenon. This will be, you may have heard of the 6 degrees of separation, the fact that you can get from any one person in the world to any other person just by going through personal acquaintances. The reason that works is that human relationships form a small world network. This was quite graphically demonstrated in the 60s by a guy called Stanley Milgram, who demonstrated it by, in the United States, took a bunch of letters, several hundred I think, put the address of somebody in Cambridge, Massachusetts on those letters, and gave those letters to a bunch of just random people, I think in Kansas and some other Midwestern states. And the instructions were, you've got to get this letter to the person whose address is on the letter, but you can only do it by sending it to someone you know personally. And they need to send it to someone they know personally, and so on. And what he discovered, quite amazingly, is that these letters not only found their way to this guy, but typically when they did so by going through, I think it was an average of about 6 or 7 people. So you've got a country of 270 million people, and this simple routing algorithm in a totally decentralized way, just relying on personal relationships between people, was able to get from one person to another in just about 6 steps. Very powerful, very scalable, and very robust. If one person decided to be malicious and send the letter to someone completely unrelated, then it would actually it would basically restart the routing process, and it would take a little bit longer, but not significantly longer. So very robust against failure as well. And this is the basic principle that most totally decentralized peer-to-peer networks rely on in order to find information. The thing about a small world network, though, is you've got a bunch of people, or more generically, you've got a bunch of nodes, and some of them are connected to each other. But even though small, short paths between pairs of nodes might exist, that doesn't necessarily mean that you can find them. In the case of human relationships, if you think about what those people were doing, they get a letter, they look at it, they think, Cambridge, Massachusetts, I have a friend who lives near Boston, I'll send it to him. So they're routing on the basis of who do I know is most likely to know this guy, and to make that decision, they're relying on geography, they might think about profession, a whole load of rich information that people have that allow them to route effectively. So that's how people find short paths. But that's not necessarily so easy for computers. In order to find these short paths, you need a concept of similarity between nodes in your network. You need to know that, well, you're trying to get to this guy in Cambridge, Massachusetts. You know this person who lives near Massachusetts, therefore they are close together in a certain sense. It also needs to be the case, and this is somewhat self-evident in the example I've just given, but peers which are closer together have to be more likely to be connected to each other. The whole reason that you send something to your friend in Cambridge, Massachusetts is because since he lives closer, he's more likely to know that guy or know somebody who does. And so the algorithm in this kind of small world network is extremely simple. At each step, you just think, who do I know is closest to the destination I'm trying to get to, and that's who you send your letter or request for information or whatever it happens to be to. We call this approach greedy routing. So this is the basic principle that Freenet and distributed hash tables rely on.
Okay, so what we're dealing now is with the second generation networks, where we want to build this dark network that Ian described in the beginning. We want to build a network like Freenet, but we want it to be possible for people to only have to communicate with their trusted friends in the network. In order to do this, we have to use this theory about the small world that we just described. So the question is, how can we then apply this theory, these ideas from this experiment that everyone in the world is closely related, and try to use that to make this network where people only have to talk to their trusted friends. And the first thing we need to realize is that in order to do this, we need to have some way of accessing information in the network. And in the old Freenet, in the old peer-to-peer networks, where computers would talk to each other at random, and you didn't have any control over who your computer was talking to, you could just go on somewhere on the network and grab the file from somebody, or look up in an index or whatever. So they're always building links between computers. But in this case, we don't have that. We only have this social network of people and their friends to find something. So we need a way to look through this social network in order to find data or find things on our network. So in other words, we need a way to route through the network just like one would on the internet. And on the internet, of course, there's a system of routing which depends on IP addresses and all that kind of stuff, where the IP address tells you which network it belongs to and then what host on the network. And this is a very hierarchical system that then allows you to route onto the thing. But, and these numbers then are assigned according to some plan. There's a whole plan of people who actually assign internet addresses so that the system works. Whereas in our case, we have this social network which is completely unplanned, completely chaotic, yet we have certain properties, and we want to find some decentralized way of searching in this network so that we can find the data we're looking for in the dark peer-to-peer network. And of course, Ian just described that we had this Milgram experiment where people were given a letter and they were asked to forward it by only sending it to acquaintances. And it turned out that this is pretty much exactly, this is pretty much exactly what we want to do in the dark network. We have a network that's set up with links only between people who know each other, and we want to be able to send a message from one side to the other in order to access some data or communicate in some way. And so if people were able to do this, they were able to find a way to send this letter to the correct person, even though he was on the other side of the United States, then sort of we could hope that there is actually a way that computers could do this as well, just perhaps, in seconds rather than days, because we want it to be useful. And to do this, we have to look at sort of what are the dynamics, what is the mathematical situation in a network which allows this to be the case. And this goes back to the small world properties that Ian was talking about. And in particular, there's an explanation by computer scientist John Kleinberg at Cornell, who showed the kind of dynamics that a network needs to have in order for it to be possible for this type of greedy routing to actually find paths quickly. In order for it to be possible in this graph to just say, okay, we need to go in that direction, and then we just try to always go as near as we can, and hopefully we'll find the thing in a short number of steps. So it turns out that that the possibility of being able to route possibly depends essentially on this property that there are connections of different lengths. Most of your connections are to people who somehow surround you, your neighbors, your close friends, who then somehow are near you in some overlying space. But sometimes there are long connections that go far away. So somebody in Germany has a friend in New Zealand or Brazil or something, so that we can make long steps, but most of them are short, so that once we get close to somebody, it becomes more likely that they actually know the person that they are near. And there needs to be a very specific relationship between the amount of short and long edges of different lengths in order for this type of routing to be possible. It needs to be that sort of as you get further and further away, the probability that you know someone will decrease, and it has to be that the probability of these links or friendships occurring has to be inversely proportional to the length of the friendships. And in that case, we actually have this simple greedy routing where we just say, okay, we have a position, we want to go somewhere, well, we'll just send it to the right person, and we'll get it. We'll just send it to the person who's closest to our destination, and then it should get through in the steps that are about on the order of log squared of n, which is usually pretty good in these types of situations. Anything that's log tends to be good. But the problem is, of course, that this greedy routing depends, you want to say, okay, we're going to make it go closer, but we're dealt here a completely social network. We're told who knows who, because each node in the darknet knows which its friends are, but we have no idea about where people are, about who they were. We can't say that sort of thing. So there's no easy way to answer if the person is closer to another. There's no easy way to answer these sort of questions, which we end up having to ask. We know we want to send a message to Harry, and I have two friends, Alice and Bob. And the question is, of course, if I want to apply this greedy routing, I should just send to the person who's closest to Harry in some sense. And that sense might be the geographic sense, or it might be, but just I want to send it to who's the most likely to know Harry. And this is not a question which directly has an algorithmic answer. So if you go back to the experiment that people did where they're sending letters, and you actually have this letter, and you know it needs to go to Harry, and you're trying to decide if you want to send it to Alice or Bob. Well, you might look at where do they live, what do they do, what do they work with, and try to see which of those two is going to be the closest to Harry. But in practice, when we ask the computer to do this, we can't really do this. And there are several reasons for this. For one, it's rather impractical to try to think of a metric that the computer would use to try to see how similar are two people. And for the other thing, of course, we have to remember that our thing here is that we want to build this anonymous file sharing network. And with our users, if the first thing that happens when you install it is, oh, would you please insert all your personal information so that we can route, they won't be very happy. So we can't really do that. So instead, what we have to do is we have to take the network, which is all that we've been given, and use that to tell us where people belong in the world's social space, and then we can route based on that. So we're going to show this in a second so that you get a very clear visual idea of what we're doing, but just to outline it first. What we know is that this model of how a navigable small world network looks is that for this to work, there needs to be few long connections and many short ones. And sort of as the connections get longer, they need to get less and less likely to occur. So people who are far away from each other need to have few connections between each other. People who are close should have many. So what we try to do is that when people join this network, they're given a position or a numerical identity. And this is assigned in some grid. And then we try to assign these in a way so that we actually get this property that people who are close together conceptually in the world's social space somehow, people who are likely to know each other, will end up close together, whereas people who are far away in the world's social space in some way end up far apart in this thing. And then, so another way of looking at this is that we have the world. So in some sense, there is some space which everyone in the world belongs to, and mostly maybe geographic. You know, you tend to know people who are close to you, who live in the same city or in the same country. But there's also the other things, like you tend to know people who do the same thing, who might come to Chaos Computer Club meetings or something like that, even if they're from far away. So we need to try to reverse engineer these positions of people in the world based only on what each person knows, and we need to do it in a decentralized way because all the time we don't want anybody to have global information. Everyone has to, at their point, just do some calculation and decide where they should be. And once we've done this, then we can return to the greedy routing case and just say, well, now we have positions, and if we want to find somebody, we just they have an address that we can just route to by just looking at our neighbors and saying, well, which one is closest to the destination? And that's where I'll send my message for them. So in general, there's a very simple algorithm to do this, which is when people join the network, they're given a position at random. So at first, everyone just chooses a position at random. And this will result in something very unoptimal, because if you've just chosen a position at random, you and your best friend, who would be likely to know many of the same people, might still end up on the opposite sides of the network. But then there's a switching algorithm by which people switch their positions, and they switch positions with other nodes, and we do this in a way so that the people so that people who are close to each other in the world social space should end up close to each other in their identifiers. And now we should try to run this graphical demonstration so you can see this in practice.
This is the fun bit, hopefully.
So everyone who's asleep can wake up.
Yeah, wake up. Okay, so let me just explain what you're looking at here so you understand what's about to happen. We have a network here. It's a 15 by 15 network where we have a bunch of nodes. Some of these nodes are connected to each other. Some of these nodes are not. So if you imagine each of these nodes is a person, each of the lines you see connecting nodes is a friendship. between those people. Or more accurately, each of these nodes is a Freenet user. Each line between Freenet users are people who trust each other and who have a direct connection between each other. Now, we have arranged this network such that it has a small world structure according to what Kleinberg tells us the small world structure needs to be. And you can tell that because here at the bottom, we have a histogram which shows the number of links of each length. So you can see that we have a lot of very short links, and as the links get longer, we have fewer and fewer. And that actually corresponds pretty much exactly to what Kleinberg mathematically tells us is an optimal small world network.
So even though this is randomly generated data, it's randomly generated using the dynamics that we expect a social network to have, which is that each node here, there's these points that are connected, represents a person. And in this very, I mean, this isn't small world, this is a tiny world since it's only 15 by 15, but that's only because we can only show so much. The point is that people who are close together here will tend to be friends more often, because being close together on this represents being neighbors or being people who belong together somehow in the world. So we have this density of most people who are next to each other will know each other, but people on opposite ends of the thing will most probably not know each other. There are fewer people who know each other far away. And this is the kind of dynamics which you can see if you take a look at real social networks. This is the kind of thing that you have. Of course, you might not have, what you might not have is where the points are, which brings us.
So, what's good about this, what Kleinberg tells us, is that in this kind of network, greedy routing works really well. And if I do that, you can see what we've tried to do here is, starting at the top left, we've tried to route down to the bottom right. And you can see that, just using greedy routing, you can see that that actually happened in just 1, 2, 3, 4, 5, 6 steps. So that's pretty good. So this well, it doesn't prove anything, but it shows that in this kind of small world network, greedy routing works really well and can typically get from A to B quite quickly.
Yeah. So there's no cheating going on here or anything. We just taken 2 points and we try to find a route between them. And at every step, it's just taking the neighbor that is closest to the destination according to this grid. And there's no. So, and you can see that, in fact, here, it seems to be a very good route, because at every step, it's getting closer and closer to the destination, which is the sort of what you would expect, because the dynamics of this network actually makes this sort of routing very effective.
So what we're going to do now is screw up this network, I hope. OK. Now, it's very important to note that this is the same network. We haven't disconnected any nodes that were connected, and we haven't connected any nodes that were disconnected. It's the same network. All we've done is we've randomly rearranged the positions of all the peers in this network. And you can see the effect that this has on the histogram. Instead of the nice small world histogram where it started high on this side and went down, now we've got what is essentially a random distribution here.
And this represents sort of what we're given in the beginning with our dark network, because while we are given this sort of network of people's connections to each other, we don't have this global overview knowledge that we had before of who belongs next to whom. So we end up just having a graph which we've just thrown in the positions randomly to begin with, and it will look like this, where you don't see this dynamic of people being close to each other, being more likely to know each other. In fact, we have edges going all over the place because we just didn't know where people were supposed to be.
This is basically when Freenet starts, this is kind of what it has. It knows who's connected to who, but it has no idea what their locations are. It has no idea who should be closer to who else in order to achieve a nice small world architecture. And we're going to prove that this sucks by demonstrating what happens when you try to route between 2 nodes in this network. And you see that it basically bounces all over the place. Greedy routing simply doesn't work.
Because you have none of the dynamic of the fact that I'm getting closer to somebody doesn't make me more likely to know them here. So the greedy routing, in fact, makes no sense whatsoever, because the whole thing with the greedy routing is we want to get close because that'll make it more likely that we find someone who knows the person. But here, routing greedily is just really the same as a random walk, because we're just bouncing around randomly until it does run into somebody who knows the destination.
Okay, so just for the purpose of illustration, we've taken one node in this network and we've highlighted the other nodes that it happens to be linked to. Since this is just a random distribution, you'll see that these links are all over the place. There are very few short ones. There are a lot of really long ones. This is not the kind of thing we would hope to see in a small world network. Now, what we're about to do is apply our algorithm, the swapping algorithm, to this network in order to rearrange the positions of the nodes in this network, again, without changing who they're connected to or not connected to, just changing their locations in order to try to get back to a small world link distribution. Now, this algorithm is completely decentralized. It can be implemented in a completely decentralized way. In fact, we have implemented it in a completely decentralized way. In Freenet, we'll talk about that later. But the goal of this algorithm is to take a bunch of people. It knows who is connected to whom. It has no concept of where these nodes were originally. It's got to try to rearrange them in order to get back to a small world network. And here we go. So the algorithm is running.
So you can see two things happening now that you should be aware of. The first is that the histogram here starts to look more and more like it did originally, with many more short edges than longer, whereas we did not have it. And the other thing, of course, is that the green one, which had really long rays coming out of it, is now being rearranged so that it's getting closer and to its neighbors, whereas before it was very far from its neighbors. It's finding a way to send in around them. And of course, also, you can see that the network itself is beginning to look more like it did originally than just the jumble that it was when we had rearranged it.
Okay, so we keep iterating here. It'll stop in a second. This is the algorithm that we will use with Freenet in order to assign these identities, these locations, which in Freenet is basically a very large number, to peers in the network in order to reverse engineer which peers are closer, in some sense of the word closer, that somehow maps onto social relationships, such that we can greedy route through this Freenet small world friend-to-friend network in an efficient way. Okay.
There's one. Show the route as well.
Yes. Okay. And as you can see, we try to. This is actually routing between the same two nodes that we did the initial route between. And you can see that these nodes now have a different location. They have been moved. Our algorithm hasn't got back to the same configuration these nodes were in before. However, it has achieved a small world link distribution, and as a result, you can see that it's able to route in a pretty small number of steps. So the algorithm has succeeded. Okay. We'll upload this. This is just Java, a simple Java thing we hacked up yesterday. We'll upload it to the Freenet website so that people can play with it. Okay.
So just to establish now that this demonstration we did is not the only indicator we have that this algorithm actually works as we'd like it to, we're just going to show some results from bigger simulations, where we've done simulations of very large networks rather than this sort of 225 node tiny little network that we did up here. And so I'm going to compare the random search, which is just walking around randomly looking for someone, with the way a greedy routing would work when the network is generated, which is always going to be very good. And then we're going to look at our algorithm, how close can we get back to the original thing after doing about 2,000 iterations per node of the algorithm. And the successful number of queries within this log squared of n number of steps is you can see that when you're doing a random search, as you'd expect it, as the size of the network grows, and I believe it grows up to 512,000 nodes here, you can see that random search simply can't be successful within that number of steps. We're only talking maybe 100 steps at most, whereas the greedy routing really always works. You can see the green line, which is just up at 1, because the dynamics there really work. If you have generated a network with these type of small edges, you can really just find where you're going. And then going from a screwed up network back using this algorithm, we can see that we've restored almost all the way up the success value. It's only at the very end there at the 512,000 that we have some failures. And this basically just means because a network which is that large needs to run longer than my computer wanted to run it. And if we look at the length of the successful routes, we can see the same thing, that in the random case, it looks very bad. You have to take very, very long routes, and of course, we were only successful a very small amount of time, whereas in the good case, it's only less than 10 steps the whole time. Even up when you have 500,000 nodes, you're only taking 10 steps to find where you want. Whereas in the restored case, we can bring it almost all the way down. So we're taking maybe 20, 25 steps at most. And that was, of course, simulated data. And what we showed you in the graphical demonstration was also simulated data in the sense that we've just generated a network that has this dynamic that we're looking for. And that then one would expect to be able to work because there's good mathematical reasoning why this algorithm should work on such networks. What about if we take data which is actually from a social network? So the first bit of data that we used this on was data we borrowed from Orkut.com, which is Google's social networking thing. And yeah, so starting from in here, we took out about 2,196 names and yeah, broke our EULAs. And the people in the set had about 36 friends each, so it's rather dense. And as it turned out, because we started with Ian, it tended to stay around the techies. So mostly Americans, but some Europeans. It wouldn't surprise me if there's somebody in this room who was, except for Ian, of course, who was in the set. I wasn't, though, so not popular enough, I guess. And it had this sort of degree distribution, which you might think is also true of social networks, which is that there were a few people. Most people had only some 20 friends or something like that, whereas some people had very, very many friends, so up above 200. So, and one can then compare sort of the best way previously, which has been suggested to search these sort of networks, is actually just to walk around randomly and hope that you find the person you're looking for. And of course, in this sort of network, I mean, in this case, because it's dense and because it's this degree distribution, random search actually works pretty well. You can, in about 43 steps there, you found 72%. So, I mean, I'm saying this is good, but of course, it's not practical. You'd never want to run something if you take 43 steps to find something. The latency would be horrible. But still, and I should go back. Our, on the other hand, was able, using the algorithm, running it for a while against this data set, giving people positions, and then routing based on that, we could do it in about 7.7 steps, 97% of the time. So we feel that this is rather indicative that this really does work on real social networking data. And just to show that it isn't about the fact that there were these stars who knew so many people, we clipped the degree, by which I mean we don't allow anyone to have more than 40 friends. And then we can see that the random search suffers badly because it doesn't come through these people where it has all these friends. But on the other hand, our thing only increases by a couple of steps and the success rate stays the same. So it isn't really depending on such people.
Okay, so really what we've been talking about so far has all been about theory. And one of the, I guess, differences between us and other people is that we're actually putting this theory into practice. We have an open source project. We have implemented the algorithm we've just described in open source software in Freenet, although so far it's still at a very early stage of testing. But building this kind of thing, making it practical is the real battle. Kind of getting the theory to work is, you know, it's not easy, but if the theory works brilliantly, but nobody can use the software, you know, it's not a success. It's not a success for us. So when you're implementing this type of thing in practice, what are the problems? Well, how do you prevent malicious behavior? Anyone can join this system, provided, of course, that they know people that are already members that are willing to connect to them. But what happens if they try to disrupt the network in some way? What happens if, with this swapping algorithm, they try to abuse it by pretending that they have a location they don't have, or so on and so forth? How do we make sure it's easy to use? How do you come up with an easy to use way that people can find each other and agree to connect to each other and then tell their computers what their computers need to know in order to facilitate that connection? This is not a small problem. Look at something even like PGP is a good example, which came out years ago, which to software engineers it's pretty easy to use, but it never really entered mainstream usage just because it's not easy enough. And with Freenet, the bigger the network is, the better, and we really can't afford just to be limited to a relatively small number of tech-savvy people. We need to make sure that Freenet can be used by as many people as possible. And of course, there's another aspect of Freenet is data is stored on, data is actually cached on people's computers in the network. Okay, so just breaking down each of those. What are the dangers? Well, if you have a certain identity, a certain position in the Freenet network, if you get to choose, that will determine what information is cached on your computer. So if you can choose your identity, you can actually have an influence over what data people ask you for, people try to find on your computer. And so if you want to censor that data, then it places you in a position to do that. So we need to think about how it may never be possible to make that, to defend against that kind of attack 100%, but there are steps that can be taken to make it much more difficult and to make it require a lot more effort. And similarly, if you can also manipulate other nodes' locations in the network, it allows you to disrupt the routing process as well. How do we ensure ease of use? Well, there are a couple of difficulties here. Peers, in all peer-to-peer networks, it helps if people leave the peer-to-peer software running. But that is particularly true of this architecture because you may only be connected to 5 other people. If none of those people are online and you want to access Freenet, you're not going to be able to do that. Now, of course, in some situations, if people are just going to switch their computers off at night or whatever, and there's just nothing you can do about that. But there are steps in terms of usability that you can take to make it easier for people or to make it more likely that people will leave the software running. And so we need to think about that from a usability perspective. Similarly, how do you introduce peers? In Freenet, obviously, if you want 2 peers to talk to each other, they need to exchange their IP addresses on the internet. Additionally, we want them to exchange some cryptographic information so that they can recognize each other and to make port scanning for Freenet nodes more difficult. But this is basically a block of, to most people, unintelligible data that they need to exchange with each other and then somehow tell their Freenet nodes about. How do we make that happen in as painless a way as possible? Do we encourage people to send it by email and then cut and paste? Or how do we do that? And that's, that's one of the usability challenges we're looking at. So can it be done by phone? Well, it'd be a long and rather dull phone conversation, but in theory. Or can you rely on a trusted third party? From a usability perspective, that's actually by far the easiest way to facilitate this, if there's a third party that can be trusted. But of course, that creates exactly the kind of centralization that we hope to avoid in Freenet and in most anonymity preserving software. Also, what about NATs and firewalls? Now, these things are a nightmare for peer-to-peer. A computer behind a NAT or a firewall is essentially like a telephone that can only really make outgoing calls. Fortunately, the way firewalls are implemented, there are ways that you can get around this problem by using certain characteristics of how firewalls handle UDP. Now that's not really a hack. We're not doing anything that causes a firewall to do anything that a firewall doesn't want to do. A firewall wants to prevent connections from people that you don't want to talk to. But using UDP NAT circumvention, the only way you can end up talking to somebody is if you essentially want to talk to them. So this is not a security risk, even though we are kind of circumventing what NATs try to do. So this is the technique that's used by Digger, which is another piece of software of mine, and Skype, which many of you will probably be familiar with, a very popular voice over IP application. In fact, a voice over IP application that I think a lot of its success comes from its use of this technique, because in my experience, certainly with voice over IP software, one of the biggest problems is you have to go in and reconfigure a firewall, and it's just a mess. The issue with NAT circumvention is that it does require a third party in order to negotiate this direct connection. But that third party can be, pretty much anyone in the network that's not behind a NAT or a firewall. So it doesn't need to be a single centralized third party. It can be anyone else in the network. Okay, so in conclusion, I think we'll have some time for questions. We believe it's possible to do what we're trying to do, and we are doing it. We're well underway to implementing this. You can go to freenetproject.org. All our source code or most of our source code is under the GPL. It's all under a free software license. And we're very keen, particularly if you're a Java hacker, this is all written in Java, and you're interested in being part of this, check out our website, find our IRC channel. It's #Freenet on Freenode. Say hi, and if you're actually willing and able to contribute, and you get your teeth into something, it's very easy to start working on this stuff. We're not a very exclusive organization. We welcome anyone that's willing to help. But going back to the theory of this, there is still work to do on the theory. The algorithm we've described, we know it works in simulation. Evidence suggests that it works on small world networks with our ORCID tests, but we don't know that it's the best possible algorithm. There may be much faster and much more efficient, much more robust ways to do this, and that is an ongoing topic of research for us. Can we find better ways to choose peers to switch? Right now, when we're deciding whether or not two peers should switch, they're just chosen at random. Maybe there's a better way that we could choose two peers to see whether they should switch than simply choosing them at random. And of course, we need to test it on more data. Practice is always more difficult than theory. This is something we've learned very much the hard way over the past 5 years. And in the next version of Freenet, Freenet 0.7, which will incorporate what we've been talking about here, we've really tried to apply a lot of the lessons to avoid a lot of the mistakes that we've made in the past. But still, you know, I'm sure we're going to discover a whole new set of mistakes that we've made. So you can never underestimate the difficulty of actually implementing something, particularly peer-to-peer networks. Okay, so as I said, that's our website. Check it out. There's a lot of information on there. Join our mailing list. Join our RSC channel, and you can help us out, hopefully. So I think we may have a few minutes for some questions.
Okay. So at the moment, you're using a flat 2D coordinate system, but that's an entirely arbitrary choice in this case. You could use 3 dimensions, 4 dimensions, or you could use 2D on a sphere. Have you experimented with any other coordinate systems?
Well, actually, the 2D thing was, we did it now in order to make it visually appealing. In fact, what we're using is a one-dimensional system where we place everyone in a ring. That seems to be the one that's most computationally feasible. And we've run simulations both on the social network data, the thing that we showed, and also there are other social network data we can use, like the PGP set and stuff like that, to try to see which one of these seems to be the best. And it seems to be that they were actually, 1 dimension, 2 dimensions seems to work about the same. Then you start going to 3 dimensions and stuff, it doesn't work as well. Probably more to do with the problem being more computationally difficult than the data fitting worse. So there's sort of, but it's a very good question, sort of, and that's what we meant when we said there could other models work better. The question is, what should you be fitting against? And who knows what the real world looks like? It probably isn't a flat 2-dimensional grid. It probably isn't a 3-dimensional thing either. It's something very complicated. What we really just need is something that works good enough. And in fact, it seems that a circle is actually good enough. So.
Cool, thanks.
You're building this network of friends. What I don't understand is, at the end of the day, if there's a direct connection between 2 nodes when they're trying to exchange a file, how will that be useful in concealing that you're using the network?
That's a good question. So so it doesn't create a direct connection between peers that are exchanging files. Rather, the file is transmitted along a path, along the path that the request took.
Okay, so really you need the friends you're connected with, they shouldn't be firewalled, because you said circumvention of firewalling is a problem. But as long as you're connected to nodes that, well, along the path, I suppose you need it to be as least firewalled as possible, because it will have to go at least 6 steps to any other node in your network, and if there's a blockage on the way, you won't get the file. Is that correct?
Right. I mean, well, there could be more than one path, so it's a robust system. So you tend to, but of course the point is, we all know firewalls are a problem for peer-to-peer software. Wherever you have 2 peers who try to talk to each other, if they're both behind firewalls, then you get problems and you end up having to use these sort of hole punching techniques. So in a way, these systems are more firewall friendly than the old type of peer-to-peer systems, because you know who you're talking to. So if you have 10 friends that you trust, those are the ones you're going to be sending packets to, and you can keep a sustained connection to them the whole time. Whereas in old peer-to-peer systems, the kind of open ones, you get connections going all over the place. So in that sense, this thing is more firewall friendly. But on the other hand, we really need people if two people are trusted friends, they really need to be able to talk. Because if half the trusted friends can't talk, then this will not work. That's why we worry about firewalls when it's...
Thank you. Any other questions?
Let's say someone on the upper left wants to talk to someone on the lower right. So there's this chain, and person A sends to B, sends to C, until eventually it arrives at the destination. And I suppose all that is encrypted because all peer traffic is encrypted. But does every peer along the way decode the packet and re-encode it? Or how do two people which are more than one hop away establish secure communication?
So it is link level secure communication. So yes, every peer along the way decrypts the request, which they need to do because they need to figure out where to route it next, and then they will re-encrypt the request. There is other crypto going on. The request is encrypted before it's even sent into the network, and what you're actually trying to find in Freenet is the hash of the key that you're looking for. So it makes it not impossible because it's still vulnerable to a dictionary attack, but it makes it a lot more difficult for intermediate nodes to know what data is actually being requested. So the key of the data and the data itself is encrypted between the person who actually inserted the data and the person who's requesting it. And only the person, the originator of the request, can decrypt the data. This is a thing which we call SSKs, and unfortunately, I'm not sure there's going to be time to explain exactly how it works, but there's kind of two layers of encryption, link level and then this higher layer.
So there would always be link level and end-to-end encryption on these sort of things. That would be.
Okay, but does this usage of social network, isn't this a problem in creating profiles? I mean, you want to hide this information, usually who talks to whom and who knows whom, and you're actually encouraging this. So often someone is only interested in who knows whom. For example, if I'm a resistance guy in China and my 7 friends are also in the resistance movement, it's very easy to track me and my friends, isn't it?
Well, certainly if one person can be identified, then, you know, and they're actually going to break into their home and, you know, look at their computer or do a detailed study of their internet connection, yes. Well, yes and no. I mean, the chances are that there'll be much easier ways under those circumstances for, let's say, the Chinese government to determine who your friends are. But our goal is actually to prevent it from getting to that stage, to prevent, so that using this system, there's no easy way for somebody to determine that you're part of this system. Once they are looking at you and willing to expend manpower specifically to attack your anonymity, you have much bigger problems, I would say, because they can break into your home when you're not there, they can bug your keyboard and all sorts of things. Our goal is to prevent it from getting to that stage.
There are limits on how much you can protect against in practice. There's no software we could write which could help people in North Korea, sort of. I mean, there's some point. So what you're looking at is rather this sort of thing is, with current peer-to-peer systems, with current Freenet, well, you have, if somebody, you can just join the network and start harvesting, finding out people who are in there and start attacking them. And people might have heard that this has been going on with some file sharing networks. So, whereas with this sort of network, you would really have to use a technique where you can't just come in and get lots of people. You really have to try harder. So, and all you can really expect to do is make it harder for people. So that's. But on the other hand, of course, there is a trade-off that with this darknet, you're really showing who knows who, and even to somebody in the. Like, there's been questions about these identifiers we're assigning. Maybe they tell, like, wow, he belongs with the resistance because his identifier is around. You know, so there is a legitimate question about that. But this is the way you kind of have to do it if you want to route in one of these networks.
A question, what about agents that infiltrate the net of trust, so that some people from agencies say, oh, we are the cool geeks, and you and you are invited, and they lead you into some means of yes, they spy on you, and then they want to harm you.
Well, then, I mean, it's the responsibility of the user that if they're saying, I trust this person to know that I'm part of this network, if you're going, you know, and some guy sends you an email from like something at FBI.gov and says, hey, I'm a cool hacker, want to connect to Freenet through me, then it's kind of your own fault. I mean, there is a responsibility on the user to, if you're told, you know, find people you trust to connect to, and you connect to a bunch of people you don't really trust or you shouldn't trust, then, you know, it's kind of your own fault.
Okay. Whenever you're communicating, you always end up having to trust somebody. And there are lots of these anonymity networks around and all that, and they tend to, oh, we're going to protect you and you don't have to trust anyone. But the truth is, whatever you do, they always end up with somebody that you have to trust. And in most of these systems, you end up having to trust some centralized third party, whether it's the person who gives you the nodes that you're connecting to in your anonymity network or something like that. You end up having to trust these people. So. And what this does is not that it takes away the element of trust. You can still get screwed if your friend screws you, but you decentralize it so that everyone is only trusting the people they use. So I got this from somebody who, after discussing this with me, said an analogy is everybody trusts their mother, but not everyone trusts my mother. So we have a decentralized trust system where, yes, people can get, I mean, you can't stop people. If your friend turn on you, you're in trouble. But at least there isn't some point where somebody can come in and turn on everyone.
You're not being forced to trust a stranger. You have to trust your friends. Surely it's better to trust your friends than to be asked to trust a stranger.
Okay, but history shows that some groups were screwed up by trusting friends.
Well, get better friends. I mean. It's not a perfect system, but it's better than what is available to people today, and that's really the goal. If the goal is, and this is something you get a lot in anonymity systems, you know, people kind of say, hey, but wait, it's not perfect. And, you know, that's the problem with that is that if you wait for something perfect, then in the meantime, you've got a bunch of people using something that is a lot worse than the imperfect thing that you could be offering to people. So of course, the goal is always perfection. But if you just wait until you've achieved perfection before you release anything, then you'll never release anything. And, you know, you're not helping anyone by doing that, because today people are using architectures which are a lot less secure than this architecture, you know, even though this architecture has still not achieved perfection.
Yeah.
Hi. Thank you. I think we need to...
I have a quick question, but I'll just ask you in person afterwards. I mean, just to say that I work with some of the type of organizations that you mentioned, and so I think this is really great. The thing is, how do you use the transmission, in not just for web, but for email and things like that as well? So I'll...
Yeah, well, you can use it for other things as well. We discussed the Freenet application of this sort of thing, but you can definitely do point-to-point routing and that sort of thing as well.